Hello and welcome to this FMSP online revision recording for the OCR specification module M1 Mechanics, and the topic is equilibrium of a particle. Under that heading in the specification there are 5 sections. The first one refers to identifying forces and particularly the relationship between mass and weight. In other words, that weight equals the mass in kilograms times g, where g is the acceleration due to gravity, 9.8 meters per second squared, and that gives a weight in newtons. Secondly, that a particle is in equilibrium if and only if the vector sum of all the forces acting on the particle is 0. However, it's often very convenient, if we know a particle is in equilibrium, to use the fact that the sum of the resolved parts in any particular direction will be 0. The third statement is concerned with smooth contact, in other words, making the modelling assumption that there is no friction involved in the contact between a particle and a surface. And obviously this is a limitation because it's a modelling assumption that simplifies the mathematics of the problem, but maybe in real life we'd get a slightly better answer if we considered the frictional forces involved. Section 4 involves contact between two rough surfaces. Firstly, there's the normal contact force or the normal reaction force that's perpendicular to the plane, for example, when an object rests on a plane. And if surfaces might move against each other, there's the frictional force. And we understand that F equals mu r is the maximum value of that frictional force. If the particle is in limiting equilibrium, then F max applies. But the friction might be less than mu r if, for example, the force that the friction is opposing is smaller than the maximum value of the friction, in which case the friction doesn't need to take its maximal value. And lastly, a reminder about Newton's third law, in particular that where there is contact, there are reaction forces involved. So let's look at some key points, and this can't be emphasized enough. You need to draw a big clear diagram showing all the forces and make it big enough to enable you to draw on resolved components of forces. The typical error I see is diagrams so small that it's hard to draw on all the components that are needed. So aim for 1/3 to 1/2 of a page when you draw your diagrams. And then, if we're considering equilibrium and taking the resultant force in any direction, shall we consider horizontal and vertical? Well, if most of the forces are in those two directions, yes. On the other hand, we might choose parallel and perpendicular to the plane if we have, for example, an object at rest or moving on an inclined plane. And then a word about normal. Normal reaction doesn't mean the usual or the typical reaction. Normal in this case specifically means at 90 degrees or perpendicular, usually perpendicular to a plane when an object rests on a plane. Reaction forces occur when any objects are in contact, and that's Newton's third law. And a little reminder, we've already talked about friction, but the value of friction might be 0. If it doesn't have to oppose any other force at all, then friction could take a value between 0 and its maximal value. So it could be 0, it could be something in between, it's just enough to resist motion. However, if we're told that a particle is in limiting equilibrium, or if it's moving, then F is definitely taking its maximal value. So read the questions carefully. Here's our first question. A small smooth ring R of weight 7 newtons is threaded on a light inextensible string. So here's the ring R on a string that runs from A to B. Its weight is downwards, 7 newtons, and it's pulled to the side by a force of 5 newtons, making the string tight and giving us the angle ARB of 90 degrees. these two tensions are going to be equal, and it's the job of the first part of the question to explain why they're equal. We're given pretty strong advice to resolve horizontally and vertically, which means resolving the two tensions into components. And we'll be enabled by that to form two simultaneous equations for t cos theta and t sin theta, which we shall solve and find t and theta. Now I'm going to redraw the diagram because this line here, RB, is so close to vertical that it's rather difficult to show the components when I resolve that particular tension. So here's my attempt at redrawing that diagram. First of all, there was a line across the top, and now I'm going to exaggerate the slope of this line from B to the ring, and now I'm going to draw in the rest of the triangle. So there's the point A, and here's my ring at R and the weight force of 7 newtons. Okay, we have tensions in the strings either side. It is a continuous string, that's important to say. And we have an angle theta here, which I'm going to chase around the diagram in just a moment. There's my other force of 5 newtons to the right. Okay, if the angle at B is theta, and if this angle, now rather pulled out of proportion, is 90 degrees, then the angle at A over here is 90 minus theta, which of course is 180 minus 90 minus theta. Okay, now let's look at theta. If this angle is theta, then the angle in there is also theta by the Z rule, or by alternate angles. And as I need to resolve the left-hand tension into components, let's also drop a vertical line down there through the point where the ring is at R. And if this angle is 90 degrees, then if at A it's 90 minus theta, and here is a right angle, this part of the angle by R is also theta. And now I can start labelling on components. For the one on the right, I'm going to split the tension into a component here and a component vertically. The one next to the angle will be t cos theta, and the one opposite the angle t sin theta. And then for the other tension, I have a vertical component here. Try and squeeze in the writing, t cos theta, and across here t sin theta, because this one is opposite the angle. And now I'm ready to start answering the question. The first part concerns why the two tensions are the same. Well, it's because the ring is smooth and free to slide along this string. If you could hold the string in such a way that the two tensions were different, as soon as you let go, the ring would slide to a position where the two tensions were the same. So, I think the key words are that it's a smooth ring, and secondly, that it's free to slide. Okay, now let's resolve forces horizontally and vertically, and because the situation is in equilibrium, we're equating forces. Lefts equal rights and ups equal downs. Horizontally then, to the left we have t sin theta, and to the right t cos theta and the 5 newtons force. Vertically, upwards I've got t sin theta and t cos theta, and downwards 7. So t sin theta plus t cos theta equals 7. And there's my two equations. Now I'm going to solve these simultaneously to find theta and t. First of all, as equation 1 is written in the form t sin theta equals, I think I'm going to substitute using that equation for t sin theta in equation 2. So equation 2 becomes instead of t sine theta, t cos theta plus 5, and then the rest of it plus t cos theta equals 7. So I can remove 5 from both sides, subtract 5 from both sides, and then let's put the two t cos theta terms together. That's 2 t cos theta, and of course by dividing both sides by 2, t cos theta equals 1. So there's a nice simple statement, I'll call it equation 3, about t cos theta. Well, let's substitute that back into equation 1. Equation 1 says t sine theta equals t cos theta plus 5, but I know t cos theta is 1, so that's just 1 plus 5, which gives me t sine theta equals 6. Again, a nice simple statement, and using those two I'll be able to solve to find t and theta. So I have t cos theta equals 1, it's equation 3, and t sine theta equals 6, which is equation 4. Well, I'm sure you've seen this done before, but if I take equation 4 and divide it by equation 3, I'm going to get tan of theta. So let's write it out slowly and show that. Equation 4 is t sine theta equals 6, and I'm dividing that by equation 3, t cos theta equals 1. Well, the t's cancel, and sine theta divided by cos theta is tan of theta. Tan of theta equals 6 divided by 1, which is 6, so theta is tan to the minus 1 of 6, and theta equals 80.5 degrees. And that is a steep sort of angle, like the one in the original diagram. Now, I could use that value of theta and substitute it back into either equation 3 or 4, but it's a better strategy if I can, in an exam, not to depend upon a calculated value if I can go back to the original source. So instead of that, I'm going to do equation 3 squared plus equation 4 squared. So squaring the left hand sides, I've got t squared cos squared theta plus the left hand side of number 4, t squared sine squared theta. And squaring and adding the right hand sides, 1 squared plus 6 squared. Well, of course that gives me t squared as a common factor on the left. Let's take that out. That leaves cos squared theta plus sine squared theta. And on the right, 1 plus 36. Well, as I'm sure you know, cos squared plus sine squared equals 1. So the left hand side is just t squared times 1, just t squared. So t squared is 37, t equals the square root of 37, and given that the square root of 36 is 6, this must be just a bit bigger than 6. In fact, it's 6.08 newtons to 3 significant figures. And there we go, we found theta and t, and that concludes the first question. Okay, this next question is quite long, and I've chosen not to do part B, which involves repeated use of the Suvat equations, which really fall under the category of kinematics, which is covered in another revision recording. So I shan't do that part, but I do want to do the first two parts because they involve resolving parallel and perpendicular to a plane. So let's look and see what we've got. There's a log being winched up an inclined plane by a tension in the cable, and our first job is find the tension in the cable. We're told the acceleration, we're told the value of mu is 0.15 and the mass of the log is 600 kilograms. So the winch is in operation and we have an acceleration up the plane. Now I'm going to redraw this diagram because the 10 degrees angle is so shallow that it's hard to show all the resolved components. So I'm going to exaggerate the angle so that I can show everything I need to clearly. In the second part of the question, we're going to consider the cable breaking, and with the log already moving up the plane, we're going to consider what slows it down, show the deceleration of the log whilst it's continuing to move up the plane is 3.15 meters per second squared. There's our task then, and I'm going to do this by, first of all, redrawing the diagram. So I'm going to exaggerate that angle of 10 degrees, make it a bit more like 30 degrees on mine, but call it 10 degrees of course. Then we have the log of mass 600 kilograms, and of course the weight force acts downwards. As I'll be putting in the resolved components on the right hand side, it's easiest to label the weight on the left hand side of this arrow. And then of course I have the tension in the cable up the plane. Because it's being winched up the plane, a frictional force down the plane. So this one's tension, this one is friction. And as the block is in contact and resting on a plane, there's a normal contact force, a reaction force. I typically use R for reaction force, and I know some other teachers use N for normal contact force. Use whichever you prefer, of course. And we have a value of mu of 0.15. When it's being pulled up the plane or winched up the plane, we have an acceleration of 0.11 meters per second squared. Now let's resolve these components. This angle will also be 10 degrees, and so the component opposite the angle will involve sine of 10 degrees. It's 600g sine 10 degrees. And then for the component next to the angle, it's 600g cos 10 degrees. Now we have everything ready to start considering our forces. And firstly, I'm going to resolve perpendicular to the plane. That's my sign for perpendicular, a little right-angled symbol. Perpendicular to the plane. And I'm doing this because I'd like to establish the value of R, because I'll need that for the friction. R, upwards from the plane, out of the plane, and in the other direction, the only other force is 600g cos 10. That's R sorted. Well now, since the log is moving, must be the maximum value of friction. So friction is mu R in this case. Mu is 0.15, and I've established already that R is 600g cos 10. Well, calculating all of that gives me 869 newtons to 3 significant figures. And that's the value of the frictional force. Make sure you store that information. So I have that, and when I use it in future I'll use the fully exact value. Don't make the mistake of writing answers down to 3 significant figures and only using the rounded version in subsequent calculations. Well, that's perpendicular to the plane. Now let's consider parallel to the plane. And because the log is moving up the plane, I need to use F equals ma. Don't forget, of course, that F equals ma. The F there isn't a single force, it's the resultant force in the direction you want, and we've got 3 components to consider parallel to the plane. Firstly, T up the plane, but also down the plane, the frictional force. And if it's in the opposite direction to the acceleration, I'm taking here the acceleration as what defines the positive direction. So the friction is in the opposite direction, 869 newtons. Minus, now there's another component down the plane, and it's this one. It's 600g sine 10. That's equal to the mass of 600 times the acceleration of 0.11. So that right hand side works out exactly to 66. And on the left here I've got t minus 869 minus, and I've calculated a value for this, it's 1021, but again I'm keeping the exact value on hand so I can use it in a moment. So let's add everything to the right. T equals 66 plus 869 plus 1021, and carefully using the exact values I had for that 1955.65, etc. So my value of T is 1960 newtons to 3 significant figures. Now then, that's part 1. I just want to consider part 2a. This is the part that asks if the cable snaps, so there's no longer any tension up the plane, but it's immediately after the cable breaks, so the log is still moving upwards, which means the friction is still down the plane. What will slow down? What will decelerate this log? So I'm going to consider the deceleration. If I'm considering deceleration, I'm going to consider the forces down the plane. So parallel to the plane, what have we got? We've got the friction of 869, that still applies. And also acting down the plane, we have the 600 G cos 10. Sorry, 600 G sine 10 degrees. And this is equal to the mass of 600 times A, which in this particular case means deceleration, because I'm taking the direction down the plane as positive. Well, that gave me 1889.65 equals 600A. And carefully using the most accurate answers I have, I divided through and got the acceleration to be, I should say the deceleration to be 3.149419. Yes, I think I'm pretty convinced that the acceleration down the plane, or the deceleration of the particle, is 3.15 meters per second squared to 3 significant figures, as they say in the question. Good, that's that question finished. I've chosen the next question because it's rather long and looks complicated, but actually, carefully done in stages, it isn't that hard. This is the first part of the question. A block lies in limiting equilibrium with some forces. Of course, if it's in limiting equilibrium being pulled to the left, there'll be a frictional force to the right, and of course there's weight downwards and reaction upwards. Now I'll do all of this properly in just a moment, but once you've found the coefficient of friction between the surfaces, the next part of the question says, what if the block is sawn in half to make 2 smaller pieces, so that the force of 4 newtons applies to the bottom, the 5 newtons to the top, and now find the coefficient of friction between those 2 surfaces. And then for a third part, assuming instead that the value of the coefficient of friction between the 2 parts of the block is 0.1, what are the accelerations of the 2 separate blocks? Now I think this sounds like quite a threatening question, so I want to take it apart and just show that it's nothing like as hard as it first appears. Okay, let's look at the first part again. We have a force of 5 newtons which will resolve into parallel horizontal and vertical components. We have a friction to the right and reaction upwards, weight downwards. We want to find the coefficient of friction between B and the surface. Okay, let's get all of that on the diagram, see what we can do. So my first note is that it's in limiting equilibrium. Therefore, the friction we're talking about is mu r. In other words, rearranging that, mu is friction divided by r. By the way, I've passed over the question quite quickly. Don't forget you can always pause the recording and read the question more slowly if you wish. Now then, this block has a 12 newtons weight. That means, should I want to know the mass, I'll have to divide by g to work out the mass. There's a friction acting to the right, because it's being pulled to the left. I'd like to find the value of mu. Because the block is resting on a surface, there's an upwards force here, a reaction force I'll call r. And then I want to split this 5 newtons force into two components, one upwards and one to the left. I'm just going to move that 5 to make it the hypotenuse of the triangle, so we can see very clearly that this is 5 sine 60 because it's opposite the angle, and this component is 5 cos 60 because it's next to the angle, and there's a little right angle in there. Now I've written on everything I need, let's start considering horizontal and vertical components, and I'm going to begin with vertical so that I find the value of r first. So vertically, upwards I have r plus 5 cos 60. That's equal to the only downwards force, the 12 newtons weight. Well, rather conveniently, cos of 60, as I expect you know, is 0.5. So 5 cos 60 is 2.5, and I've got r plus 2.5 equals 12. That means I can simply take 2.5 from both sides and get r equals 9.5 newtons exactly. And therefore, if I want to consider my horizontal components, well, to the right I have friction, and to the left I've got the 4 newtons force and the component of the 5 newtons force, which is 5 sine 60 to the left. Unfortunately, 5 sine 60 isn't such a tidy thing, and simply calculating this gives me an answer of 8.33 newtons to 3 significant figures. And again, store that answer because we shall use it later on. Well, I can now calculate mu. Mu is equal to Fr divided by r, which I wrote back up here. And I know both of those as numbers. 8.33 divided by 9.5, and that gives me a value for mu of 0.877 to 3 significant figures. In fact, I had 0.876, 855, etc. before rounding. Well, that's found the value of mu for this first part of the question. Now let's look at this stage where the block is cut into two pieces. And the significance of this is the 12 newtons weight has been cut into two pieces, a mass at the top which now weighs 9 newtons and a piece at the bottom which weighs 3 newtons. So if I need to know the mass of the piece at the top, it's going to be 9 divided by g, so that 9 divided by g times g will give me the weight of 9 newtons. Significantly, this force acts on the lower piece, and we have friction still with that same value of mu that we found acting at the bottom, but for the top block the 5 newtons force acts, and the friction here is the friction between the two parts of the block in contact. So for those two surfaces in contact we need to find the value of mu. We're told it's in limiting equilibrium, so we are equating coefficients, we are equating components in order to do that. And then for the last part of the question we're going to take instead a value of mu for the coefficient of friction between the two parts of the block to find the accelerations of the two separate pieces. Okay, let's concentrate on the top block only to start with. What forces are acting here? Well, it's resting on the block below, so there's a force up here. I've used N this time to differentiate it from the R that I used before, and there's a weight force acting downwards of now just the 9 newtons. On this block there is the friction acting to the right. That's different to the previous friction. I'm going to call it FR dashed, and that's based on a value of mu for those surfaces in contact between the two parts of the block. I still need my two components of the 5 newtons force, and they're, as they were before, 5 cos 60 and 5 sin 60. The 4 newtons force is not acting on the top part of the block. Okay, so this is just for the upper part of the block. And let's see what we have. Well, again, let's do vertically. Upwards, we've got the normal contact force upwards plus 5 cos 60. And that's equal to the 9 newtons downwards. And as before, 5 cos 60 is 2.5, which means we've got an exact value for N of 6.5. That's newtons. I know it's slightly confusing, but I've used N for the normal contact force as well. Okay, now let's consider the friction by looking horizontally. Well, I've got to the right this new frictional force, and what can we say about this frictional force? Well, it's equal to mu times that normal contact force N. Well, mu I'm trying to find, but N is 6.5. That's mu there, excuse me. There we go. So let's use that in my equating coefficients. And I think perhaps it's misleading writing H there. Let's write it again here. Horizontally, what have I got? Since it's in limiting equilibrium, I have the friction to the right, which takes its maximal value, is equal to the only force to the left, which is 5 sin 60. Well, what do I know about the friction? Down here, I've written that the friction is 6.5 mu, and that's equal to 5 sin 60. So mu is equal to 5 sin 60 divided by 6.5. And I can just calculate that, and I got a value of 0.666. Well, we'll leave that auspicious value of the coefficient of friction behind, because for the final part of the question they say, what if mu between the two parts of the block is 0.1? So let's do that to finish with. Okay, let's consider the lower block first of all. And what we're asked to find is the acceleration of each block. So, firstly, for the lower block. Well, what do we know? We already know what the friction is, and it hasn't changed because the total mass sitting on the surface hasn't changed. So the friction to the right, or at least F max, perhaps I'd better write F max in there, is equal to 8.33 newtons. And that's unchanged from the first part of the question. But the force to the left is 4 newtons. Well, that means that actually it's not going to move because the friction is sufficient to resist that motion. Let's write that nice and clearly. Since 4 is less than 8.33 newtons, no movement. So actually the acceleration for the bottom part of the block is 0. That was simpler than it first appeared it might be. And now let's consider for the upper block what happens. And bear in mind we knew the weight of the upper block was 9 newtons, which means that the mass of the upper block is 9 divided by g kilograms. Okay, we were given a new value of mu. Mu equals 0.1. So from that we know that the new friction is mu times n, and n hasn't changed. That's still 6.5. So it's 0.1 times 6.5. That gives me a new value for the friction of 0.65 newtons. And by the way, we know the mass of the block. So let's use F equals ma. And we have the force to the left. Don't forget I haven't drawn the components on here. The force to the left there is 5 sine 60. That's going to be resisted by the force to the right, the friction, and that's the friction acting here. That's my FR dashed of 0.65. And in total that's equal to the mass, which is now 9 divided by g, times the acceleration that we're trying to find. Well, I think let's multiply both sides by g over 9. This gives us quite a lot to calculate. Let's just put all of that in the calculator and see what we get. And I had an answer of 4.0072, etc., which means it's 4.01 meters per second squared to 3 significant figures. And I hope you feel that although this looked like a complicated question, taking it a stage at a time, it wasn't so bad after all. And that concludes this recording. And don't forget to look at the others in the series.